Differential equations. Our objective is to solve differential equations and applied problems modeled by differential equations. An equation of the form dy dx equals f of x is an example of a differential equation. Notice the word differential, like differentiable, refers to derivatives. So this is an equation that has derivatives in it. Whether it be a first derivative, second derivative, it's an equation that involves a derivative. That is a differential equation. Any function y equals capital F of x plus c, for which dy dx equals f of x, is a general solution of the differential equation. Notice that there are no derivatives in the solution. So we think of a solution of a differential equation, we think that there are no derivatives left. We've solved it. We've made the differential part of the equation go away. A particular solution is the solution to the differential equation where the value of c is known. So a general solution has the plus c. The particular solution is when we found the c and now it is an actual value, not an arbitrary constant. We will find c using the boundary condition or initial condition. It could be called either of these. The boundary condition or initial condition is a point on the graph of the solution used to help find c. Let's look at some examples. For numbers 1 through 2, find the particular solution of each differential equation having the given boundary conditions. Verify the solution. Number 1, dy dx equals x squared plus 2x plus 1. When x equals 3, y equals -1. So remember, a solution of a differential equation is when we get rid of the derivative. So to get rid of the derivative, we take the antiderivative. Taking the antiderivative of dy dx takes us back to the original, what we call it, y. Take the antiderivative of each of these terms one at a time. Remember that we add 1 to the exponent using our power rule, leaving some space in front. That makes x to the third, and then we multiply by the reciprocal of the new exponent, 1/3. Plus, 2 is a constant multiple. It hangs out in front. Leave some space. Add 1 to the exponent. We don't see an exponent. That means it's 1. Adding 1 to that is 2, so x squared, multiply by the reciprocal of the new exponent, 1/2. The antiderivative of 1 is x. If we think about it backwards, the derivative of x is 1. And then our arbitrary constant plus c. Let's clean this up a bit. Y equals 1/3 x cubed. 2 divided by 2 is 1, so that leaves us x squared plus x plus c. Because there is a plus c here, this is called our general solution. But we want the particular solution, which means we need to find the value of c. We do that with the given boundary condition. The boundary condition is this point here. When x equals 3, y equals -1, we plug this in to the general solution. Y is -1, so I plug -1 in for y. When x is 3, 1/3 3 cubed plus 3 squared plus 3 plus c. Notice how c is the only unknown left. I can solve for c from this equation. So let's clean this up to solve for c. -1 equals 3 cubed is 27, divided by 3 is 9, 3 squared is 9, plus 3 plus c, that gives us -1 equals 21 plus c, and therefore c equals -22. So now we can write the solution where we know the c. Y equals 1/3 x cubed plus x squared plus x minus 22. This right here is our particular solution because now we know the value of c. Let's check our answer by verifying the solution. How do we verify that this is our solution? Well, we see if it works by plugging it back into the original equation. The original differential equation has a first derivative, so let's take the first derivative to verify dy dx equals, what's the derivative of 1/3 x cubed? 1/3 times the derivative of x cubed, 3x squared. What's the derivative of x squared? 2x. What's the derivative of x? 1. And what's the derivative of negative 22? 0. So 3 divided by 3 is 1, and I get x squared plus 2x plus 1, and that is what dy dx is supposed to equal. We verified the solution. Number 2 involves a second order differential equation. What that means is we have a second derivative as the highest derivative in this equation. D squared y dx squared, or the second derivative of y with respect to x, equals 12x squared. When x equals 0, y equals 1. When x equals 3, y equals 8. We're going to solve this differential equation. Remember, to solve means to find an equation that has no more derivatives. But if we have a second derivative, first we have to get to a first derivative. So we'll go from the second derivative to the first derivative, dy dx, by taking one antiderivative. 12 is a constant multiple. We'll leave some space, and now we do the antiderivative by adding 1 to the exponent, x cubed, and multiply by the reciprocal of the new exponent, 1/3, and of course we have a constant, plus c. Let's clean this up a bit. 12 divided by 3 is 4, so we actually have 4x cubed plus c. Now we have to do this process again because we still have an equation that has a derivative in it, a first derivative. So we have one more antiderivative to do, which means we're going to end up having another arbitrary constant. So to keep it straight, let's call this constant c sub 1, and our next constant will be c sub 2. The antiderivative for dy dx, y, equals, looking at this, 4 multiplies to the antiderivative of x cubed, where we add 1 to the exponent, get x to the 4th, and multiply by the reciprocal of the new exponent, 1/4. The antiderivative of a constant, c sub 1, is the constant times x, and then we have our next arbitrary constant, c sub 2. Because remember, we still have 0, and to get 0, we need a constant to take its derivative to get that 0. Let's clean this up a bit. 4 divided by 4 is 1, so 1x to the 4th plus c sub 1x plus c sub 2. Now, we don't want these constants because we want the particular solution of this second order differential equation. So we'll use our two boundary conditions. Let's start with the first one. This boundary condition where x equals 0 when y equals 1. So we plug in for y, 1 equals x is 0, so 0 to the 4th plus c sub 1 times 0 plus c sub 2. It looks like we can solve for c sub 2 from this equation. We get c sub 2 equals 1. Let's use our other boundary condition. When y is 8, x is 3, so 8 equals 3 to the 4th plus c sub 1 times 3 plus c sub 2. Now we do know that c sub 2 is 1, so we can plug that one in as well. So we get 8 equals 81, 3 to the 4th is 81, plus 3 c sub 1, and c sub 2 is 1. So 8 equals 81 plus 1, 82, plus 3c sub 1, subtract 82, negative 74 equals 3c sub 1, dividing by 3, c sub 1 equals negative 74/3. Now we can write our particular solution where we know both of the c's. Y equals, Looking back to our clean particular solution where we didn't know the constants yet, x to the fourth, c sub 1 is negative 74 thirds, so minus 74 thirds x, and c sub 2 is 1 plus 1. There's our particular solution. Now remember our directions asked us to verify. So we do that by taking the derivative. Looking at this equation, dy dx. The derivative of x to the fourth is 4x cubed. The derivative of negative 74 thirds x, negative 74 thirds, and the derivative of 1 is 0. Remember, our original differential equation is second order, so we need the second derivative. The derivative of 4x cubed is 12x squared, and the derivative of 74 thirds is 0, and this does match our original differential equation. Looks good. Number 3, the acceleration of an object is given. Find the distance s of the object from the origin under the given initial conditions. Now remember that distance is a measure of position, so we often call that p, if that makes you more comfortable, and the relationship between position and acceleration is that starting with position, we take the derivative, we get velocity, we take the second derivative, and we get acceleration. So velocity is first derivative of position, and acceleration second derivative of position. So we could rewrite this if we wanted. So a of t, instead, we could call it p double prime is 8t minus 3. This initial condition says the position at time 0, whether we write it as s sub naught or s of 0, is 1. So this means when t equals 0, the position equals 1. The velocity, v sub naught, or the velocity at time 0, v of 0, equals 4. So we can think when t equals 0, that velocity is 4, or p prime equals 4. They gave us acceleration, and they're asking us to find the distance from the origin, or the position. So we have to go from a second derivative to no derivatives. We have to go to the first antiderivative to go from p double prime, and we'll get to p prime. 8t, 8 is a constant multiple. The antiderivative of t is t squared times 1/2 minus the antiderivative of 3 is 3t, and the antiderivative of 0 is the arbitrary constant plus c. Now, because we have to go from a second derivative to no derivatives, we're going to ultimately need two constants. So let's call this c sub 1. We'll clean this up a bit. 8 divided by 2 is 4, so 4t squared minus 3t plus c sub 1. Now we can find that constant by using our first initial condition. Oh, wait a minute. That initial condition has to do with position. We want the initial condition that has to do with p prime, or velocity. So this is the one we're going to use first. P prime is 4, so 4 equals when t equals 0. So 4 times 0 squared minus 3 times 0 plus c sub 1. Those are both 0, so c sub 1 equals 4. Let's rewrite our equation. P prime equals 4t squared minus 3t plus 4. Now we'll take the antiderivative again to get to position, or just p with no derivatives. P equals, 4 is a constant multiple, add 1 to the exponent, t cubed, and multiply by the reciprocal of the new exponent, 1/3, minus 3 times, add 1 to the exponent is 2, multiply by the reciprocal of the new exponent, 1/2, plus 4t, plus our second arbitrary constant in this problem, c sub 2. Let's clean this up a bit. So p equals 4/3 t cubed minus 3 halves t squared plus 4t plus c sub 2. Now we can use the initial condition that has to do with p, the position. P equals 1 when t equals 0. 4/3, 0 cubed, minus 3 halves, 0 squared, plus 4 times 0 plus c sub 2. Each of these are 0, so we get that c sub 2 equals 1. And now we'll write our position equation. P equals 4/3 t cubed minus 3 halves t squared plus 4t plus 1. And there is our position equation where we know all of the constants. Thanks for watching.